Neural networks. In this session we'll see what is neural network, what is the vocabulary of neural network, what is the neural network algorithm and the real mathematics behind the neural network algorithm, how it works, building the neural network, what are some of the applications of neural networks, how do we validate the neural network. Finally we'll see one of the examples of neural network, that is image recognition using neural networks. So we will try to see some simple intuition towards understanding neural networks. Neural network is known as one of the black box methods. That means the theory behind the method is not very obvious. So it's not that easy to understand neural network or visualize neural network, but we'll try to use few examples and intuition of logistic regression to understand neural networks. So let's do a quick recap of logistic regression. What did we learn in logistic regression? So when there is an output which is yes or no, 1, 0, let's say there is a binary output and the predictor variable is continuous, then we can't fit a linear regression line. Then we tried fitting several lines and we found logistic regression is better compared to linear regression line. It suits best to the data set. So we fit a logistic regression line for this data. Now we'll try to understand neural networks using logistic regression, but before that let's do a quick recap of how do we build logistic regression, or how did we build logistic regression, and how are we going to build a neural network based on combination of several logistic regressions. So let's do a quick lab. So in this lab we have to take employee productivity data, then filter the data set, take a subset from the employee productivity data. The filter condition is sample set less than or equal to 3 or less than 3 actually. So draw a scatter plot, age on x-axis and experience on y-axis. Try to distinguish two classes with two colors. Looks like there are two classes of people in this particular data set. Build a logistic regression model to predict a productivity using age and experience. So we need to predict productivity using two variables, one is age, the other one is experience. Finally, draw the decision boundary for logistic regression model. Okay, create the confusion matrix, calculate the accuracy and error rates. Let us see how do we do that. So here is the dataset that we are talking about, employee productivity dataset. It's a small dataset just to have an understanding of the logistic regression and some other related concepts like decision boundary. So this is just for a demo purpose. We have created a dataset. Now we need to take two samples of this data, sample 1 and sample 2. Sample 1 with the condition there is a variable called sample set. If we see the variables in employee productivity, the names of employee productivity are, there are three variables, age, experience, productivity and sample set. Sample set is just to identify what type of what sample is it, what data set that we belongs to. So we want to take sample set less than 3, so sample set takes 1, 2, 3 values. So we want to consider sample set equal to 1 and 2 as one data set. So this is the data set employee productivity 1, and how many observations are there in employee productivity 1? There are 74 observations, 4 variables. What are the names? These are the 4 variable names, and this is the kind of head of that data set. Now we want to see the number of the frequency of the dependent variable in this particular data set, that is productivity 0, it takes 33, 1, there are 41 values. Now what we need to do here is we want to show a classification graph. So what is a classification graph? We want to see how many ones are there, how many zeros are there. So 1 is in the form of triangle and 0 is in the form of a dot. So there are, like, as age is on the x-axis, experience is on the y-axis, we can see there are few ones and few zeros. Looks like they can be classified very easily. So we'll try to fit a logistic regression line the classifier and see whether that can help us in classifying zeros one from ones, or putting a decision boundary between them. So I'm going to fit a logistic regression on productivity using the variables called age and experience from this data set family equal to binomial, since I'm going to do a binary logistic regression. So this is giving us a logistic regression line with intercept, age and experience respective coefficients. So these are the coefficients of the model. We'll quickly go ahead and create the decision boundary. To create the decision boundary, we will find slope and intercept. So this is slope and intercept. So let me draw the decision boundary. So on this particular graph itself, what is this logistic regression line telling us? So what is the, where are the ones and where are the zeros? How can we classify using logistic regression line? So on this particular graph itself, I'm going to add logistic regression line decision boundary. So this is the logistic regression line decision boundary. Anything above the line is 1, classified as 1. Anything below the line is classified as 0. Looks like fairly accurate model, except 1 or 2 points. We have classified everything correctly. We should get a very high accuracy. So in the confusion matrix, most of the values should be around the diagonal, yes, apart from 2 points of zeros, 2 points of ones are wrongly classified, and the accuracy is fairly high. So this is a very good model with an accuracy of 94%. So that is what the lab was all about. So we wanted to create a decision boundary for this particular logistic regression model, and then create a confusion matrix and calculate the accuracy and error rates. So in all classification algorithms, decision boundary is what we are looking for. So basically, which class falls in what side of the decision boundary. So the line or margin that separates the two classes is called the decision boundary. So in every classification algorithm, it's all about finding the right decision boundary, and it's not mandatory that the decision boundary need to be straight line or linear all the time. And here in this particular example, the function for our decision boundary is y equal to class 1 when w transpose x plus w naught is greater than 0. This is nothing but x1 beta 1 x1 plus beta 2 x2 plus beta naught greater than 0, or else class 0, or else y equal to 0. So in logistic regression, we can very quickly or simply convert the logistic regression line into decision boundary. So this is the logistic regression line that we are talking about. Y equal to probability of y equal to e power beta naught plus beta 1 x1 plus beta 2 x2 divided by 1 plus the same equation. So in that, if we suppose the probability, anything with the probability more than 0.5 is 1, class 1, anything less than 0.5 is class 0, or vice versa, then if we substitute 0.5 in there, we can clearly come up with a line which is b0 plus b1 x1 plus b2 x2 equal to 0. That is the equation of the straight line that we got as the decision boundary, and we can simply rewrite that equation and say that if x2 is greater than this particular value, then the particular y value is class 1, y belongs to class 1. If x2 is less than this value, then it is class 0. If x2 is exactly equal to this value, then it's a tie probability of 0.5. So this decision boundary is created by using the threshold value as 0.5. We can slightly modify the decision boundary by choosing a different threshold value. So we have already seen how to create the decision boundary for a given logistic regression. So in our particular logistic regression, we can see that our decision boundary on the right hand side of the decision boundary, or on the top portion of the decision boundary, everything is classified as 1. On below it, everything is classified as 0. And to find the decision boundaries, we created the line. To create that line, we first found the slope and the intercept values. So here is the slope and here is the intercept. They are all found based on the formula that we just observed.